Okay, so keep the end goal in mind. Remember, we're still talking about this SN2 reaction with bromooctane and your salt solution, okay? And we analyze this by GCMS. We just went over the mass spectrometry parts, so we have to go over the gas chromatography part, okay? So this is the actual instrument that analyzed our compound, and at the end of our GC was the mass spec part, okay? So we have to talk about the GC. So this is what a GC kind of looks like on the inside, okay? So you put your sample in here, and this nice helium gas will kind of sweep it along inside the column, and things will separate on the column, okay? The GC separates things based on boiling point. On boiling point or volatility. Okay? If you have a low boiling point, then you're going to pass through the column a lot quicker, okay? And you're going to go into the mass spec, okay? So the GC is really just the part, it's called a gas chromatograph because it uses gas to kind of sweep your sample along, and the lower boiling you are, the less you're going to interact with the column, okay? So this is just the same as our stationary and the mobile phase. The mobile phase here is our gas, and the column is the stationary phase. So if we have a low boiling point compound, you are not going to interact with the stationary phase very much, and you're going to get swept through the GC very fast into the mass spec. Okay, so there's our mass spectrometer. We already went over all that. So again, it separates things based on boiling point. Okay, from here, the lowest BP will come off first. BP comes off column first, okay? Highest BP last. Comes off last. Okay? So, here we go. These are the mass spectra corresponding to the different products you could see in your solution. Okay? So, here in the different mass spectra corresponds to either the chloride, the bromide, or the iodide. Okay, here they are. So can we figure out which spectrum corresponds to which compound? Okay, which of these compounds? Again, that's all that's going to be in here. So chloride, the bromide, or the iodide. Okay, yes, we can figure out by looking at the ions. Notice here we have a 3:1, a 1:1 ratio looking there. Hopefully there's a 127 in here. But before we even look at the ions, we could actually determine this based on the boiling point. Okay? Because if we have a shorter retention time, this corresponds to the retention time, is what I've written up here. Okay? This guy has the shortest retention time. And so it's going to be the lowest boiling. Okay, lowest BP. So which of our compounds has the lowest boiling point? Well, let's think about what affects boiling point, right? Those intermolecular forces? Well, polarity is definitely one of them, but when we have all these halides, they're definitely similar in polarity. So the main determining factor for our boiling point is going to be molecular weight. Okay? So which of these guys has the largest or the smallest molecular weight? Because remember the periodic table? It goes, actually, as it's drawn here. Cl is above bromine, is above iodide. Okay, so iodide is going to be the largest compound, so it's going to have the highest boiling point, and chloride is going to be the smallest compound, or lowest molecular weight, and so it's going to have the lowest boiling point. Okay, lowest boiling point, therefore lowest molecular weight, therefore shortest retention time. Whereas down here, okay, this is the longest retention time. Okay, 4 minutes and 20 seconds. Therefore, it's going to be the highest BP. And for us, this equals the largest molecular weight. And which compound was that? 1, 2, 3, 4, 5, 6, 7, 8. This was our iodide. Up here was our chloride. 2, 3, 4, 5, 6, 7, 8. And right here, the middle guy, 1, 2, 3, 4, 5, 6, 7, 8, is our bromide. Okay, so again, yes, we could look at the ions and deduce this same thing, and we'll go through that, but I was just looking at the retention time. Okay, this guy came off the column first. He is the lowest boiling, or has the lowest boiling point, and for our 3 halides, the main determining factor for the boiling point is going to be the molecular weight. Okay, so he is the lightest guy, so he came off first. The iodide is the heaviest guy, so he's the highest boiling point, so he's got the longest retention time. Okay, but this makes sense still. Okay, obviously the spectra here makes sense, because here you can see we have a 3-to-1 ratio of peaks. Okay, this corresponds to a chloride. Okay, 3-to-1 over here, 3-to-1 over here. Okay, here is our 1-to-1, 1-to-1, 1-to-1. This is why it definitely equals the bromide. And let's see if we can find our little iodide down here. Look at that, iodide. Okay, equals iodide. Okay, so you should be given one of these mass spectra, one of them, on your printout, which should look like this. Okay, so here I have reported the mass spectrum for the largest peak here. Okay, so we can see this is what the GC printout looks like. So this came from the GC, this is the mass spectrum. Okay, so again, each peak here corresponds to a different compound. Okay, each peak equals different compound. Okay, we can take the area underneath each peak and get percentages. Okay, area of each peak equals percent of compound in the mixture. Okay, so you can see here that there is more of this guy. It actually should have reported, or we should have given you this data. This is about 67% of our sample, and this peak corresponds to 33% of our sample. Okay, so again, as we come off the column, you can see here's the time right here. Don't worry about the abundance yet. Here's the retention time. So as the run goes, there's a little timer, and so this compound came off. This has a retention time of about 2.55. Okay, you can see here. And then this other compound came off a few minutes later. This has a retention time of about 3.15. Okay, and then there was nothing else that came off. Okay, so there were 2 compounds in this mixture. 2 compounds in this mixture. Can you tell me what they are? Just look at those retention times. Again, what will be dependent, what will determine the retention times, right? The boiling points, the boiling points. Okay, I'll let you know that the iodide comes off much later. We know that because we can look at the retention times over here. Here we go, 2.55, 3.15. The iodide comes off around 4.20. So this guy is the lightest of the guys. What is he? He is the chloride. And this guy is our bromide. So you can see here that this reaction did not go very far. Okay, we still have 67% starting material and only 33% product. Okay, so we have 67% unreacted starting material. Okay, why is that? Let's think about that in a second. Okay, and again, this mass spectrum just corresponds to the peak of the greatest height. Your data may look a little bit different, but it should just have 2 peaks. If you did this reaction, the bromide plus potassium chloride. Okay, what if you did this with the iodide? Your data should look something like this. Okay, now what does each peak correspond to? Again, each peak is a different compound. Okay, what could be the only 2 things in our solution? Right, can really only be either of these guys. This guy off to the right, he's really easy, right? This is his spectrum, and look, it's got the 127 iodide. Okay, and he came off all the way after 4 minutes. So this guy corresponds to the iodide. 1, 2, 3, 4, 5, 6, 7, 8. Okay, And so what does this guy have to be? Not to mention his retention time. Sorry, so the retention time here is about 4.20. Retention time here is about 3.15. Right? He's our unreacted starting material, the bromide. 2, 3, 4, 5, 6, 7, 8. And if you take the area underneath the curves, we get about 95% over here and about 5% over here. So you can see this reaction went almost to completion. This made a lot more product. We only had 5% unreacted starting material. Okay, so the question is why? Why do we get these differing results? Why does the KCl give us only 33% product? KCl, we only get 33% product, whereas the iodide, we have 95% product. Why? And this data is pretty representative as well of these two reactions, okay? If you look at a class's set of data, okay, in terms of those who use KCl for this reaction versus those who use Ki, we'll just say on average, if you took the average of this data, we would get generally 65% bromide to only 35% chloride on average. So about 2 to 1 bromide to chloride. And for those of you who used Ki, the average here was again a lot more product. So here the average is about 4% bromide to about 96% iodide. Okay, so again, the iodide goes a lot further to completion. We get a lot more product with the Ki as the nucleophile. So yes, the question is why? Because what is different about these reactions? Okay, let's look at that again. Right, the electrophile is the same in both of these reactions. So what is the difference? What about the nucleophiles? Good. Yes, Ruby. The nucleophile. What about that nucleophile? Do you guys see that that's really the only difference here? Is the KCl versus the Ki. So all that's different here is the I versus Cl. So go back into your notes, and which is the better nucleophile? Yes, the answer is the iodide. Okay? This guy is a better nucleophile. Why? If you go back through your notes, think about what makes a good nucleophile. First off, electronegativity. Okay? Which atom is more electronegative here? Go look on the periodic table. The chloride is more electronegative. Does that make it a better or a worse nucleophile? It actually makes it a worse nucleophile because it is more electronegative. Okay? And that's because, again, it's holding its electrons too tight. Okay? So this is a worse nucleophile because holds electrons too tight because electronegative. More electronegative than iodide. Okay, so that actually makes it a worse nucleophile. Okay, so the iodide again is less electronegative, therefore its electrons are free to go and do what they want to do, which in this case is to go attack the electrophile. Not to mention also, what else makes them a better or different in nucleophilicity? How about the size of the atom? Okay, one of the last things we talked about was the polarizability. If we're big and diffuse, again, our electrons can kind of group on one side or kind of move to one side and be more nucleophilic, just again, fleetingly, because we're big and diffuse and we are more polarizable. Okay, so again, which of these is bigger? Iodide. So again, iodide on both accounts is a stronger nucleophile. Okay, so it's better nucleophile because less electronegative and because big and polarizable. Okay, so this reaction really kind of does just is a straight up test of the nucleophilicity between the chloride and the iodide. And we can see here, based on our results, that the iodide, which gave us way more product, is a better nucleophile. Okay? Because we have in one step, right, the nucleophile just displaces the electrophile in both of these reactions, and so just based on the amount of product we can get, we can kind of judge the nucleophilicity of the iodide versus the chloride. Pretty cool. So again, the chloride gives us less product. Okay, so that is the SN2 reaction. Okay, this is the one, again, you subjected to GCMS. You got your printouts. corresponding to the amount of product in your sample, okay? And you could also take a look at the mass spectrum for each of these compounds, okay? I'll put this online. You can look at the mass spectrum for all three of them. Remember what we learned, the 1-to-1 ratio, we definitely have a bromide, 3-to-1 was chloride, and then the little 127 indicated an iodide. But we could also figure out which one of these corresponded to which product based on the retention time, right, which corresponded to the boiling point. All right, so that's the SN2.